All right, we're looking at chapter 3, steganography. That's a hard one to say, steganography. It sounds like it should be a dinosaur. So we had a lab that didn't work, and I'm gonna have, I had Copilot build me the program, and I thought, oh, I should figure out how to actually make a little installer for it. But then I have some Macs in here, so I'm not sure what to do with Macs. I'll have to find a web version of it. Anyway, I'll have it fixed by next week. So you could be surfing the internet and looking at any kind of pictures, and there could be a secret message embedded in here. In fact, they talk about that in Mr. Robot. They talk about hiding things in images. Did you get to that part?
I'm on season 4 already.
I'm 3 episodes into season 1. Does it get, I'm not gonna, don't say anything. Anyway, there's the stuff in there is what I've seen so far is very accurate as to what you'd actually do, you know?
Yeah, they're really good one in there. For one of them.
Yeah, right now, he's in the middle of like being crazy and his dad's showing up, Mr. Robot, and oh my gosh, I don't know if he's gonna survive this or not. Anyway, so you hide it in the file header fields that are used to describe the file. So metadata is data that describes data. So every time you take an image with your phone, it puts in the GPS coordinates, what time of day, lots of information about the photograph. And that's where the secret message gets hidden, is in that little space designed to hold information about the photographs.
Yeah.
If you ever, I don't know if I have anything that does that. Probably. I was just sending this to NASA this morning. They wanted a photo of me. So if you go to, I think I use this one maybe, or this one, I can't remember. This is a little old, but it's the best photo I have right now. Properties.
Gotcha.
Yeah. So that's some of the detail that how could that be in the image? This is image information up here, but how would we know about the camera that took it if it didn't have a place to store that information? And so that's some of the stuff that's put in there. And so this little extra space, yeah. I mean, look at all this. It's all the camera information, which there's no way that can be stored anywhere else. It has to be stored in the image somehow, but it's not part of the image. So that's where steganography stores its secret stuff. So yeah, there could be all kinds of things. We just wouldn't know about it. All right, so cryptography. So is this the one that I have? Oh, I don't have that in here. Okay, there is a cryptography means scrambling things. So I send a message to Owen, and if Andy intercepts it, he can't tell what's going on. So one of the original beginning cryptography things is called the Caesar cipher, which is a very classic program for computer science.
Decoder rings.
Yeah, it's called a shift cipher. I don't want to allow ads. So that means that you shift the alphabet. So to give an example of that, let me show you how it shifts. So you have your A, B, C, D, E, F, right? That's your plain text message. Well, a shift cipher means that we might start at C, D, E, F, G. So as long as I know the shift is by 3, then I can decode the message. And that's what this is doing. Here is the shifted ciphertext. Here is the code plain text. No, there. I think I typed something in there. So this will, yeah. So you can use the English alphabet. If you encrypt this, that's what it looks like. Because it's shifting it over. I can't say, oh, there it is. There's the shift number. So we can shift it over by 10. Yeah, it wants an ad block in there. Anyway, the only thing we have to transfer from me to Owen and not let Andy get is the shift number. So somehow I have to get the shift number to Owen, and maybe we have it set up ahead of time that based on the day it is, we have a certain shift number and it changes daily or something. We have to have some communication ahead of time. So that's called a shared key encryption, which is very fast. But it does require that we have to exchange information before it'll work.
And it's correct.
Huh?
And it's intriguing.
This is very easy to do, yes. But it's really quite similar to how even stuff works today. It's a mathematical calculation of some sort, and the shift is a mathematical calculation. It's a very simple and one of the original ones that does that. Oh, I thought I had that in here. There's a really good video on YouTube about Caesar ciphers.
You have the video of it. It's up there. It's just under there. It is. Right, watch cipher.
Oh, is this the,
I think that's it. It might not be the exact one you're talking about.
no, that's not
but
the right
it
one.
talked about ciphers.
This is from, wow, that's not even right. This should be connecting up to Cengage. Yeah, but I have it in another class. I'm gonna stop the recording for a second. Stop. Okay, we'll
I'm
see.
just trying to think that you have to.
It's a good logic problem.
Yeah,
I've done it several
I think you make a
times.
dictionary, I asked, and then, okay. Yeah, dictionary.
Have a list.
A list would be better, you think?
Yeah, a list.
Yeah, cause I get, yeah.
Because then you can shift the list.
Oh, and then you could just use the four, that's not fun.
Mhm. So plain text, here's some terms we have to learn. Plain text is unencrypted. Ciphertext is scrambled. Clear text means that it's never going to be encrypted. Do you suppose anything goes around the internet anymore that's clear text? Or in networks? There's just not a lot of anything that goes in clear text. Even when I was typing and talking to my Raspberry Pi, it was using SSH. It was encrypted. There's really not a lot anymore that's not encrypted unless you use ancient technologies like Telnet. That's not encrypted. FTP, the original FTP is not encrypted, but nobody uses it anymore. So here we go, the cryptographic process. We just went through that. We have an algorithm. In this case, it could be the Caesar shift. In this case, it's something different. So that encrypts it into here. We have a shared key, right? If Andy intercepts that key, then all our secret stuff that Owen and I are talking about, everybody knows about. That's the disadvantage of a shared key. The other disadvantage is that somehow I have to get it to Owen without other people seeing it. Or I have to get it to Christy or whoever else I'm sending secret messages to. That's the disadvantage. So what kind of encryption do you typically use for a wireless access point?
Like within the network or just to the access point?
Yeah, what do you do when you want to connect to Wild West? What do you type in?
Pattern.
Right, and do you have to know that ahead of time? So it's shared key encryption. And shared key encryption is very fast. Now, there's also the type of encryption that we use when we go to a website. So for example, when you go to Blackboard, do they ask for a secret key? No.
No.
When you go to Amazon, do they ask? When you go to your bank, do they ask? No. So that's what we're going to hit next. Well, it should be here pretty soon. But that's shared key encryption is used a lot. But there has to be some way to exchange those keys. And so all the websites and everything you use do use shared key encryption. But when you go to a website, there's a little handshaking at the beginning using certificates that generate one-time keys. In this case, we just keep the same key because it's complex to implement that. All right, so benefits, yep, confidentiality. This is the CIA triad. Only authorized people can view it. If I'm sending a secret message to Andy, nobody else can see it. Integrity, part of a cryptography, and does the Caesar cipher guarantee integrity? It doesn't. But there's checksums and things built into modern cryptography, which means it does a mathematical calculation at the beginning and at the end, and if it doesn't come out right, something's changed. So if you encrypt something, you want to make sure that it starts out and ends exactly the same way. So it's more sophisticated than the Caesar cipher. If you are on your banking website and you decide you want to transfer $300 to pay off your bank, and a bit gets flipped and you end up sending $3,000 and you only have 300 in your bank account, that is significant. So cryptography has to make sure that the information is correct and unaltered. Authentication means that if Andy's in his banking website and he's doing stuff in his browser, we can authenticate it that it's actually Andy. Non-repudiation means that you can't say you didn't do it. If you send me an email saying, oh, Bill, you are the dorkiest guy I ever knew, you cannot undo that. So just think about all your electronic communication. Think of it as going in, and it used to be, we used to say, think of whatever you're sending to somebody by email or whatever as something that be published in a newspaper. Well, we don't have newspapers anymore. But think of it as being in a public place. Don't say things that you wouldn't say out loud. It's interesting how many people behind the screen will be really mean and nasty. And I've had that happen with students. I get emails that are not very nice that they would never say to me in person. That's the whole like being behind a screen thing. Obfuscation is not the best approach. It's called security through obscurity. So, for instance, when I set up the Minecraft server, I didn't use the standard ports because everybody knows the standard ports. But how long would it take somebody to find that I'm using non-standard ports?
Not very long.
Not very long.
Especially if they were looking for it.
Yeah.
If they weren't looking for it, then maybe.
But that's what security through obscurity does. It took me no time at all to make that change. But it's part of that rule that I say a lot of, always change the defaults. I did not change the defaults on the fish cam. Why did I not do that? Why didn't I change the ports on this? How are we going to have people type in :444? It's not going to work. Yeah, so this is using the standard SSL port of 443, which is the standard port. But this is encrypted. You know, I have my little let's encrypt thing on here. Here it is. There it is. Certificate is valid. It renews like every 3 months or something, automatically renews. So this website had all the fishies, all their information is secret. I mean, nobody can unencrypt the picture of the fishies, which is really important. No, it's not really important, but any web browser now that goes to a site that's not encrypted, what do you get? What do you get, Christy? What do you get? Andy? Have you been to any websites that are not encrypted? What do you get? You get a big warning.
Not secure.
Yeah, the website's not secure.
Yeah.
I get that whenever I talk to, I guess I only see that because when I talk to my router, it says that because it doesn't have a certificate. I never thought of that.
That's what I mainly see. Sometimes some of the links you take us to.
And in this case, it is secure, but it doesn't have a valid certificate authority. And we'll get to certificate authorities. So would it be worth my while to set up a certificate for my internal? No, it's encrypted, but all I'm doing is changing settings and nobody's in here that's going to do anything. But on the web, everything is encrypted. Do I need to have it encrypted? Yeah, it makes a smooth experience. People don't get the warning saying, oh, this is not encrypted. Is anything on here like secret? No, there's nothing on there that's secret. But it makes a smooth experience for people to see it, and it was a good experience for me to set this up. So Let's Encrypt was actually pretty simple to set up. I had a few snafus, of course, things that didn't work quite right.
That's the nonprofit one, right?
Yeah, that's the one that's Let's
I know
Encrypt.
you talked
And
about.
WNCC just actually switched to that because it's the Let's Encrypt.
Because I was doing that assignment last time, I was like, that's pretty cool.
Oh, did I have that in an assignment?
Yeah.
Yeah, I should. I don't remember everything, but Let's Encrypt. Their mission is to make sure everybody has TLS certificates. And so there's directions in here on how do you do it, and that's what I did. I followed the directions, and you know, my fishies have up-to-date security. And it is automatically renews every like 90 days or something. And that's what we have on there. We have an Acme client that when it gets close to the renewal period, it fires off and gets a new certificate and changes out the certificate. Where's the people of? Yeah, see, all the big players are supporting it. You know, the big players are really supporting it. And the really big players are supporting it. And then you get down to here where they're just not as, you know, they're not as important. But these are all big players in the open source and other things. Yeah, and WNCC switched to using that too on their stuff. Maybe they didn't switch on the outside. I bet they just changed it internally.
I don't think I remember seeing it.
That's because this is hosted with a third party.
Yeah.
No, it's done with the same thing. And it has the same July through October, so that's about 3 months. Yeah, so it is using the same thing. Yeah, some of the things that are in here we'll see again and again, like SHA 256. That's a hashing algorithm, which we'll get to hashing algorithms. Then there's all this stuff. Yeah, there's a lot to know about security. And unfortunately, there's just a lot. Anyway, moving on. So we don't need to do a knowledge check. So we know there are symmetric shared keys. We have to exchange. Hash algorithms. Did I have an assignment for hash algorithms this semester? This one? I know I have at some point.
I don't think so.
Oh, here we go. Let's do a quick looking at what a hash is. A hash is a one-way calculator, a one-way calculation. Here we go, hash generator. There we go. So MD5 is really old, but that's fine. So if I put in my password, we'll just say this is my password. This is what gets sent over the network. It's all that scrambly stuff. Actually, nobody uses MD5 hash. This is just the first thing I found. Usually I should find something that's more current. Oh, there we go. So if we look in here, we're going to see in the WNCC site setting, oops, nope. Sorry, got to the wrong place. I need to go into the certificate. Connection is secure, certificate is valid. Do you see this SHA 256? Well, that is a hash algorithm. In fact, there it is. Oh, there it is. So a hash algorithm means that if I type in a password, and this is going over the network, like information from you to Amazon's going over the network, this is actually what's transmitted, all this goopy stuff. See how long that thing is? See how short MD5 is? SHA 256 is kind of the standard everybody uses right now. If it's too short, it's easy to crack. If it's too long, it takes extra resources and processing powers. So they always aim for somewhere in the middle. So a hash means that it's a one-way calculation. So if you have a potato and you hash it up, can you put that potato back exactly the same way it was before you hashed it? I had one student one year says, yeah, give me some super glue. I said, no, that wouldn't be the same. People use super glue. But that's the idea. It's a one-way scrambling. Well, what good does that do? If you can't unscramble it, what's the point? Right? What's the point? So when I type in a password, like when I was logging into one of my servers remotely, I type in my password, the hash of my password is transmitted to the server. The server compares my hash with the hash it has stored, and it can compare those and say, oh yeah, this is the right guy. So my password is never sent over the network, just the scrambled part, and it's compared.
Okay. That's cool.
And it's not sent in clear text. When I start, just like when we're going to Amazon, there's a little handshaking ahead of time that encrypts things so that the password is sent in a scrambled form, like the hashing form. That part's also encrypted, so no one can even get to the hash. There are ways that we can dump the hashes out of that and then look them up, and we'll do some hash cracking later on because you can using dictionary attacks, but that's what a hash does. It's a very important part of security. And it's one way. You could undo it if you have like every computer in the universe working for 50 million years. And as quantum computers may or may not, then this may change everything. I don't know. We'll see. Current state of the art is SHA 256.
So then multiple different inputs won't create the same hash, right? They will.
A good hashing algorithm means that if you change any one thing, it's totally different. Yep. So the older hashes, you can have what's called, I can't remember if it's called a hash collision, where two different inputs create the same hash. Earlier hash algorithms would have that problem with our modern hash algorithms. That's not anywhere near as much an issue. Like with SHA 256, which is our current hash algorithm, you should never have the same hash with a different input.
Okay.
And it doesn't matter if it's oh, that's the other thing I forgot to show. So notice how long the hash is. The length doesn't change. You can't tell how long whatever you've typed in is by the length of it, because it's exactly the same. And I could only tell that by looking at this one, because these other ones kind of stretch way off there. But if I type in one thing, or I type in a bunch, I do the keyboard scramble, it's still the same length. You can't tell by the length how long whatever it is that's been hashed is in there. You just see a pile of hashed potatoes. Or in real life, you'd have a bigger pile of hashed potatoes, wouldn't you? So the analogy falls down at that point. But that's what hashing algorithm. It's a very important part. There are other hash algorithms besides SHA. This just is the one that most everybody uses right now. And that will change as people start cracking these and figure out ways to get in them. Hashes are also used to make sure if you've gone to a website and downloaded something, it'll say, oh, check the download with this SHA hash. I think they do that on Kali Linux when you download it. Not everybody shows that, but let's just see. I'm pretty sure they do. Yeah, recommended. And maybe it just starts installing. Okay, they don't. But some websites will have, like, you can calculate a hash. So, and an image, which is just a bunch of ones and zeros, can have a hash. Something you download can have a hash. And you can test the download with that hash and see if it's been altered in transit or it's been changed on the server. And so hashes can be used for many things. All right, so yep. Yeah, a little super glue, we can put it back together. Now, the other side of symmetric encryption is, oh, where'd my asymmetric go? There we go, asymmetric encryption. Well, that is an issue, isn't it? If we had to call up Amazon every time we wanted to buy something and say, hey, give me my current key, that's not going to work, and that's not what we do. Here, it's one access point, we can share the key out. At home, not a big deal. But if you're Amazon, that's not going to work. So asymmetric encryption use what's called public key cryptography. Oh boy, this is like a brain teaser. So everybody knows the public key. So for instance, in my browser, I have, I don't know how to get to it in Chrome, no. Maybe
Are you looking to get to the source code so you can get to it?
Now I'm looking to get to the. So for instance, there's a public, oh, there it is. There is the public key. Okay. So every browser has the public key, can get the public key for a website. Okay. So it's done by what are called certificates. How do we get the private key so we can actually do anything? Because it's a public-private key match. So let's look at that. Everybody has the public key. The private key is only known to Amazon or wherever we're going. So how do we get the private key? Well, let's look at that. So there's something called, yeah, let's just go. All right, so this takes a bit to wrap your head around. So here I am, and Bob is sending Alice a message. We use an encryption algorithm like RSA or something like that. And we use Alice's public key. She uses it. He uses Alice's public key to encrypt the message, which looks just like the thing I was showing you earlier. It's a big, long, blah, 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 blah. It's a big, long hash. So use that to encrypt the message using an algorithm of some sort. Well, there it is. It's all scrambled up. The remote user says, well, you can scramble it with the public key. Anybody can look at it with the public key, but who's the only person that can unencrypt it? Alice is,
Private key?
yeah, Alice is the only one that has the private key. Well, is that going to work on Amazon? No, but this is a start of understanding how it works. So public-private key pairs. Let's move further. Oh, we don't need to know about, yeah, RSA is still probably what we use the most. Oh, no, we use ECC now. Anyway, that's not relevant. Key exchange. Somehow, when we go to Amazon's website, we have to find out what Amazon's private key is in order to like unencrypt things, don't we? We have to exchange things. So what we do is we eventually get to the point where we have a shared key encryption because it's very fast. Asymmetric encryption is very slow. It's used to exchange keys, and then all the information flows very quickly. So there's another piece called a key exchange, Diffie-Hellman, and all these different people. If you've done any VPNs, you've seen all these words. Not VPNs where you're hiding your surfing and all that sort of thing. VPNs where I'm at home and I want to connect to my server here at work, a work VPN. Oh, they don't finish it. What? We didn't finish the whole how things, okay, we just did that part. Okay, so we didn't go through the whole web thing. But we have to know the web thing. All right, so let's move on and finish the web thing. I didn't realize that didn't get finished. All right, so how does certificates and websites work? Oh, that's pretty good. So you have to have somebody has to be trusted. In any security situation, somebody has to be trusted. And when you're looking at Amazon and all the public key encryption, we have what are called certificate authorities. So Amazon is a certificate authority. VeriSign is a certificate authority. There's all kinds of them. GoDaddy is a certificate authority. So there has to be somebody that you trust to hang on to those public and private keys for you. Because the public key anybody can have, but not the private key. All right. So now we have our public and private key. So when we access a website, your browser receives the certificate from the website. We just looked at that earlier. It had all the little certificate things in there. It verifies the website address, matches the address in the certificate. Your web browser has a list of trusted authorities in it. That's part of what changes when you get a web browser update, is that list that says, oh, if this is a certificate from Let's Encrypt, and we can verify it's from Let's Encrypt, then we trust that website. So if somebody hacks Let's Encrypt, we're in trouble. Because they're a trusted place. If the certificate is valid and trusted, then we initiate a handshake. And let's look at the handshake. This is the part that I wanted to get to. Now we need it to be bigger than that. Open image, a new tab. It's not very big, is it? Oh, we can't even read it. Okay, we need a better image than that. Let's try this one. That looks clearer, doesn't it? Where did it go? That's better. So we've established that the certificate is good. So the client says, hello, I am okay with your certificate. I'm going to let you know what versions of TLS and SSL and cryptography that I can do. And that's the other part of the updates that happen with browsers, is it updates your encryption suite, which is everything. The server says, well, these are the things I can do. And we do an SSL testing here too to find out if your bank is up to date or not. So then the server says, well, here's my digital certificate. And then the browser says, well, okay, this looks good. Everything's secure. I'm going to send an encrypted pre-master secret. Okay, well, that's getting complicated, isn't it? So we've established a little bit of a encryption at this point. Just to get started, we send a encrypted secret to the server decrypts that and computes the session key. So if we stop Amazon and start again, the session key is different each time. Every place we go to, every time I go to lab.wncc, I have a different session key. And that's the best I understand it. We have to do a little handshaking, and once that's done, the session key is the symmetric encryption key, but it's never the same. Where every time we connect to Wild West, it's always password 01. Makes it easy to crack. This, even if you crack it, it's never going to get used again. But it does take handshaking to get started, but then it turns to symmetric, so everything happens quickly, which that's a good thing. Because nobody wants to pause or wait or anything like that when they're buying something on Amazon. They want it now.
So we're never really using a straight public-private key type thing. That's just for the initial startup and then.
That's for the verifying that they're okay.
Yeah.
That you're on the Amazon website. It really is the Amazon website. I trust what you're saying. And we have the initial public key. So the session key is kind of like a generated private key. It doesn't really, Amazon doesn't give you their private key. I don't know exactly how that works, but they never send the private key out. They use it as part of that exchange. And now we're at the fuzzy part of how I understand it.
I bet the public key is probably along the lines of like, they don't get your information like as it was, they get it as a part. Kind of like a hash.
Use the public key to
And then
verify that they are who they are, and it is a hash.
Mhm.
But your browser has a list of trusted certificate authorities, and so when it sees that key, it says, okay, you have a certificate from Let's Encrypt. Okay, I trust Let's Encrypt. Let me look up that hash. Oh, yes, Let's Encrypt says that hash is Amazon. And so you verified that you're at the right website and that you can start talking to them.
Mhm.
But somebody has to be trusted to say, yes, that certificate is good, or no, that is not a good certificate. You have to match your certificate authority, run them the little hash of the public key, and then they'll say, yep, this matches, we're good to go. So it's kind of like a password.
Mhm.
You're verifying that lab.wncc.edu is actually lab.wncc.edu before you do anything. Which is, so you can think of it maybe like authenticating.
Yeah.
All right. Phew. That was a lot. We have one other thing that we're going to take this is the interesting one. I have actually a little program we do about blockchain, and I should probably add that one to this one too, because it helps understand just looking at this until you write the little program in Python. I think that is the thing that's helped me make more sense of blockchain than anything else. So I think I'll add that to this class too.